Boom. So, all right, going to do this problem 51 here that says a child with a mass of 40 kilograms sits on the edge of a merry-go-round at a distance of 3 meters from its axis of rotation. The merry-go-round accelerates from rest, so it starts at rest and goes up to this 0.4 revolutions per second in 10 seconds. If the coefficient of static friction between the child and the surface of the merry-go-round is 0.6, does the child fall off before 5 seconds? Okay, so 5 seconds. All right. Wow. This was fun. So let's see. Couple, I'm even going to actually copy here. Move this over here like this. And paste right here. So we're going to have a, so I started off drawing kind of this. So we got a bird's eye view and a worm's eye view. Of course. So I think I'm going to do, here is at, this will be at time t equals 0 seconds, and here will be t equals 10 seconds, just to kind of show, because what's essentially happening here is it's speeding up, right? So yeah, this is kind of my initial moment here. Here's my final moment here, because there's two things that there's multiple things happening here. Because all right, what I'm trying to find out is does this so let's draw a free body diagram first. So I'm going to draw a free body diagram here. The child is spinning around. So here's the worm's eye view, so I can kind of see, like, here's the platform, here's the center of the platform. The platform's spinning it around. I don't know exactly when this is, but the free body diagram isn't really going to change that much. It's going to be the weight of the child, the normal force, and the static friction force. And the thing is that to see if this child is going to slide off, this has to be essentially greater. So okay. So now I can let's just go ahead and do Newton's second law. So F net equals ma. We got in the vertical direction, there's going to be the normal force minus mg equals 0. No acceleration in the vertical direction. So that means the normal force is equal to the weight right there. And then in the horizontal direction, you got the static friction force, which is positive because it's pointing towards the center of the circle. Remember, center of the circle is positive, is equal to the mass times the acceleration, but that's going to be centripetal acceleration. So then the static friction force at any point is going to be m times the centripetal acceleration. You might, sorry, not the centripetal acceleration, the total acceleration. Because here's the thing. It's not only moving, the child is not only moving in a circle, right, which means the child has centripetal acceleration. So there is some acceleration towards the center of the circle. That's the centripetal acceleration part. But there's also tangential acceleration as well, right? Because the child is speeding up. It's going from 0 to 0.4 revolutions per second. So, and this is always with respect to the total acceleration. So the total acceleration then is going to be the centripetal acceleration plus the tangential acceleration. So that's going to be the total acceleration right there. And just using a little bit of algebra of geometry, right? A total squared is going to equal AT squared plus AC squared. That's a Pythagorean theorem there. So this is going to be the square root of the total acceleration, or the tangential acceleration plus the centripetal acceleration. There is a lot going on here. This is a good problem. Okay. So let's see. Let's go back here. So sorry. So this is the total acceleration. And so yeah, I'm just going to stick with this for now. Another way I can calculate Fs. Well, Fs max I know is equal to the coefficient of static friction times the normal force. And we just said the normal force is equal to mg. This is actually be a separate, do it as a separate color. Let's do this over like that. So Fs max is equal to mu s times mg. I know mu s. They gave me mu s over here. So the coefficient of static friction is equal to 0.6. And we're doing this at time t equals 5 seconds. So let's hold off right there because I want to try and get established like what's going on here. So Fs max would be 0.6 times the mass of the child, which I think they gave us, 40 kilograms, times g. So times 10. So that's going to be 40 times 6, right? So that's going to be 240. So basically what I need to find out is this term here, because this is also Fs, is this, right, going to be big enough? Is this going to be big enough that Fs, that basically if this becomes big enough that it's higher than 240, then the child is going to slip off, right? Because this is the most that the static friction can make. Because other than that, then it's going to be it's going to overcome, the child's going to slip off. So I got to find out, does this term, is this going to be enough to slip the child off? So that's what I need to find out. Okay. So, all right. So now I'm going to try and calculate what the total acceleration is. I'm going to try and find out what the total acceleration is. So let's do that. Let's start with the tangential acceleration. So with the tangential acceleration. So to get the tangential acceleration, well, let's see. What I'm going to do here to get the tangential acceleration is, there's so much here. This is a good problem. It's a tough problem, but it's a good problem. So what I'm going to do is I'm going to use the fact that the tangential acceleration is equal to the angular acceleration times the r vector, right? And then I'm going to use initial velocity, final velocity, angular velocity, acceleration, delta theta, and then delta t. So I'm going to use that to find out and I'm going to try and find out what the angular acceleration is. All right. So they give me data that it starts from rest and goes to 0.4 revolutions per second in 10 seconds. Oh, and they also gave me r. R is 3 meters. So r is 3 meters, right? Because that's where the child is, right there, 3 meters. So the distance from here to here is 3 meters. That would also be the distance from here to here is 3 meters. Okay, so from rest, so I know rest, so this is going to be 0. And then I get to a speed of 0.4 revolutions per second. So let's convert that revolutions per second to radians per second really quickly. So 0.4 revolutions per second times, again, there's in one revolution, there's 2 pi radians. So this revolution cancels with that revolution, and I get, what the heck, I'll just say, no, times pi. I'll do it times pi. 2.51. So 2.51. I think I did that right. So radians per second. That's my final angular velocity. So 2.51. And I know the time, it's 10 seconds, right? 10 seconds. So I can calculate then the angular velocity. So I can, or the angular acceleration is going to be the change in omega over the change in time. So I'm going to assume constant angular acceleration. So that's going to be 2.51 minus 0. That's the change in velocity. That's the final minus the initial, divided by 10. So my angular acceleration is 0.251 radians per second squared. So I got that, but now I need to then plug it in here to find out what so yeah, gonna plug that in there to find out what the tangential acceleration is. So my tangential acceleration is going to be 0.251 times r. The r vector is 3 meters. So my tangential acceleration is 3 times 0.251. So my tangential acceleration is 0.753 radians per second squared. So I'm going to hold on to this now because this is what I need, because if I get this, I plug it in here. All I need now is my centripetal acceleration. Once I got the centripetal acceleration, I'll have the total acceleration, and then I could plug that in here, then plug everything in and see is this what the value of this compared to the maximum that force can be. All right, so let's go ahead and do that. So I got that. I'm going to hold on to that, and yeah. So now centripetal acceleration. So oh, thank you. Yep, that's meters per second squared. Good. So centripetal acceleration. Now here's where I need to be careful, because centripetal acceleration is v squared over r. Well, I know r is equal to 3 meters. That's no problem. But what speed do I plug in there, right? What speed do I plug in there? Because and how I want to find that out, because the thing is that it goes from 0 to 0.4, but it's 0.4 at 10 seconds. It's 0.4 revolutions per second at 10 seconds. So I need to find out, though, the speed at 5 seconds. That's what they want. That's what I got to find out. So what's the speed at 5 seconds? So I got to go through another. So I'm going to, again, I'm going to say that the tangential, or I could just use, yeah, let's just do this. The tangential velocity is equal to omega times r, right? So I'm going to take this and plug it in here. So that's going to make this then, so AC is omega times r squared over r. That's the same thing as omega squared r squared over r. So this cancels with this. And so so to get the centripetal acceleration, it's omega squared times r, which we've done this before. We've done that before. That's not too big of an issue. But now I'm going to do another wow fish delta theta t. So I'm going to go from t equals 0 to t equals 5 seconds. So I will still start, 0 is still going to be my initial moment, but then 5 seconds is going to be my final moment, and I'm going to try and find out what the new velocity, what the velocity is at 5 seconds. So here we go. I'll say this is 0. My time is 5 seconds, and my angular acceleration, as I said before, I said it's going to be a constant angular acceleration. So this is going to be 0.251 radians per second squared. So 0.251 radians per second squared. And I'm trying to find out what the final angular velocity is, because then I could plug that in there, and then I got this. All right. So I'm thinking the best thing to use is going to be omega equals omega naught plus alpha t. So plugging that in, omega equals omega naught is 0 plus 0.251 times the time, which is 5 seconds. So my final angular velocity is 0.251 times 5, 1.26. radians per second. So there's that. And now I could take that and plug that into this. So I'm just going to plug that in there. And again, r is 3, so my centripetal acceleration now is 1.26 squared times r, which is 3. So 1.26 squared times 3, that's going to be 4.73. So my centripetal acceleration is 4.73 meters per second squared. So there is that. So now, just to kind of zoom out here and see what I got. So I now have my tangential acceleration. I have my centripetal acceleration. And I'm going to plug that in there to get my total acceleration in order to plug that in here to make sure that this is either going to be bigger or less than this so that I can finally find out whether or not the child is going to slip off of this ridiculous, oh yeah, take the square root of it, get off this ridiculous thing, right? All right, so let's go ahead and keep doing that. So again, I'm using that the total acceleration is the square root of AT plus AC squared. Did I square those? I didn't. Ooh. Squared. Sorry about that. That should have been squared. So 0.75 is AT. 0.753. Probably don't need that many sig figs, just to be careful. And then we just found out this is 4.73 squared. Take the square root of all that. That's going to be my total acceleration. So my total acceleration, plugging in all this, is square root. I'm getting about 4.79. 4.8. Yep. Close enough. Yep. That's good. Yeah, 4.8 works too. So here we go. We got 4.79, but now I'm going to take all that, and you're going in here. So zooming back in. So again, let's say 4.8 or 4.7. I don't care, 4.79 or 4.8. So now I'm going to compare this. I'll write it in this color. So this is going to be Fs is the mass of the child, which is 40 kilograms, times now total acceleration, which is 4.8. We just found out. So Fs, Fs, force of static friction. Sorry, I guess it should have been FFS. Hopefully you guys get what I mean. It's not the spring force. So 40 times 4.8, moment of truth. 192 newtons, which is smaller. So this is smaller than Fs max. So this force that I got is smaller than FS max, FFS max. So that basically means the child is not going to slip. If it was bigger, then it would have overcome the static friction force and the child would have slipped. How are you going to set up a problem like this and not throw the child off the merry-go-round? That's silly. But yeah, anyway, that's the solution to that. So yeah, very good problem because it involves, not only centripetal, tangential acceleration, but also working with angular accelerations and Newton's second law is in there, and friction force. I mean, there is so much good stuff. And knowing what your initial moment and final moment is, I mean, because they're saying at 5 seconds, right? So much good stuff. But all right, so hopefully that helped. There you go. Something I wanted to add here, or correct here before, before posting this, is that I ended up saying that, Fs points, directly towards the center. And then I said, but this is the total acceleration in the x direction. yeah, it might have caught your eye that you said, wait a minute, wouldn't this be pointing directly towards then the centripetal acceleration? You'd be right, and that's my mistake. So, and that's because my axis is not, so my vertical axis, my y-axis still does this. My y-axis is still pointing up. So if we go with that notation, my y-axis is pointing out of the page, so there's a dot for the positive y-axis right there. But my x-axis is going to point in the direction of the total acceleration. So it's still making a perpendicular, if you can see, it's still making a perpendicular y-x, shape. But then I'm putting it here, and the positive x-axis is going this way. So the positive x-axis is going along the total acceleration. So and that would be the direction also of the static friction force. So it's not directly pointing into the center. It's kind of pointing off to the side there. So I apologize. That's my mistake. But hopefully that helps correct that for you. All right. Thank you.